Hey you all, it's Dr. Franklin, Department of Psychology, Norfolk State University, and this is a video lecture dealing with central tendency, skewness, and kurtosis. Let's start off this lecture by first answering a very simple question. What is a statistic? A statistic is a number representing a sample. There are several examples of statistics such as variance, mean, median, and mode. However, the examples may differ on the type of information they represent for a variable. For example, measures of central tendency highlight a central number that describes a variable, whereas some statistics, like variance and standard deviations, highlight a number that describes the spread of a variable. Descriptive statistics or measures of central tendency are usually the first methods used to get a summary of the data. It is possible to have distributions that have the same mean but different spreads in terms of variability. As we delve into measures of central tendency in this lecture, with lots of hands-on examples with raw data, you will see how that may be possible. This lecture will focus on the measures of central tendency, but understanding measures of variability as well will help you to understand more complex and nuanced statistics. Since this section is all about measures of central tendency, it's important to start off by defining exactly what central tendency is. First and foremost, central tendency is a type of statistical measure. It represents a single score to define the center of a group of scores or items in a distribution. So why do we need a measure of central tendency? Well, the measure of central tendency determines a single score that is the most typical or best representation of the entire group. It is important to note that there are multiple ways to determine the most efficient measure of central tendency, which we will discover throughout the course of this lecture. Looking at these three figures, it may be difficult to determine one single measure of central tendency for each graph. For each of these figures, take some time to locate the center of the distribution. The first graph may be easy to determine because it has a nice normal distribution without a skew. It is safe to say just by looking at this graph that 5 is the best measure of central tendency. This slide presents a good opportunity for a discussion of how central tendency should be characterized and how different distributions do not necessarily lend themselves to the same measure of central tendency. On this slide, we will cover how to calculate the mean of both a sample or a population. It is important that you learn these symbols and understand exactly what they represent. The mean is the measure of central tendency that takes the sum of all of the scores and divides it by the number of scores in the data set. There are two different types of means, the population mean and the sample mean. The process of finding these means is nearly identical. The population mean is represented by the symbol mu. It kind of looks like a cross between a U and an M. You find the population mean, or mu, by taking the sum, noted by the sigma symbol, the one that looks like a crooked E, of all of the scores in the sample, notes by the X. Next, you divide this by the total number of scores, which is capital N. For example, let's say all of the freshmen at a school comprised of 100 students took a math test. If you want to know the average or mean math score of an entire school on the test, you would add all of the scores together and divide by 100, being the total amount of scores. The sample mean represented by capital M is the sum, or sigma, of the sample scores divided by the number of scores in the sample. For example, if we want to find the average or mean score of just one class representing the sample of 20 students, we would add all of the sample scores together and divide by 20, representing lowercase n, also known as the number of scores. The mean can be thought of in multiple ways. As we discussed in the last slide, the mean is the sum of the scores divided by the number of scores in the data set. Another way of describing this is that the means is the amount each individual receives when the total is divided equally among all individuals in the distribution. For example, if there are 9 pieces of pie and Bill eats 2 of them, Sarah eats 4, and Eddie eats 3, the mean would be 3. 2 plus 4 plus 3 equals 9. Divide this number by the total number of participants, or pie eaters, and we get 3. It just so happens that if we split the 9 pieces of pie evenly between 3 people, the number is also 3. This is the same as the average or mean that we calculated. The mean is also known as the balance point of the distribution. It is the exact point in the middle. The frequency distribution shown is a seesaw balanced at the mean. For hypothetical purposes, let's say we have a seesaw. If we spread out all of our points evenly on the board, just like how they are represented or stacked on a bar graph, if you place the fulcrum or the triangle at the mean, it would all balance out. What would happen if we add another block right above the 5? If you said nothing, you are correct, because adding another block at 5 would not change the mean, so it remains steady. This is another example. This distribution has a population size of 5 scores that is balanced with the population mean of 7. What would happen if we add a block right above the 7? If we were to add a block to the left of the mean, a new mean would be generated, a smaller one. We would have to move the fulcrum or the mean to the left to compensate. How about if we add another block to the right? In this case, the mean would increase and we would have to move the fulcrum to the right where the new mean would be to balance it out. The next measure of central tendency is the median. If we list all of the scores smallest to largest, left to right, the median would be the point or score that is directly in the middle. Another way of explaining the median is that it is the point that divides the scores into two groups of equal size. Sometimes the median and the mean can be the same score, but not all or even most of the time. The only way to find out the median is by listing all of the scores in order and finding the midpoint. Let's try an example of how to find the median. In this example, we have an odd number of items consisting of 5 scores: 10, 5, 3, 8, and 11. In order to identify the middle score, we need to first list the numbers in order from least to greatest. Now our order is 3, 5, 8, 10, and 11. Which score is in the middle? That is correct. 8 is in the middle. 8 is our median. When there are even number of scores, finding the median gets a little more tricky. The steps are the same for finding the median for odd numbers, but there is an additional step at the end. In this example, we have 6 scores: 4, 1, 7, 9, 1, and 5. The first step is to put these scores in order: 1, 1, 4, 5, 7, and 9. When we put the scores in order, notice there are 2 right in the middle. This is because we have an even number of scores. In order to find the median, we take these 2 center scores, being 4 and 5, and we find the average. In order to do this, we add 4 and 5 and get 9. Next, we divide 9 by 2, since there are only 2 scores we are using to find the average 4, and we get 4.5. This is our median, 4.5. Although the mean and the median both look up the middle of a distribution, as we saw, these measures of central tendency define the middle in slightly different ways. Remember from earlier in this lecture, the mean is the balance point of a distribution. It is defined by distances and is often not the midpoint in the scores, but the average. On the other hand, the median is the actual midpoint of all of the scores in a given set. The median is defined by the number of scores and is not the balance point of the scores like the mean. Although they are both concepts of the middle, they are varied slightly. Here is an example to show the differences between the mean and the median. Here are 6 scores, population N of 6, ranging from 2 to 12. The median or midpoint of these scores is 2.5. We found this by listing all of the scores from least to greatest. Since 2 and 3 were the 2 midpoint scores, we had to find the average of them, being 2.5, to determine our median. The mean is found by adding all of the scores together and dividing by our sample size or our population size, which is 6, since we have 6 scores. As a result, we get our mean or balance point at 4. To summarize, this is a population of 6 scores with a mean of 4. Notice that the mean does not necessarily divide the scores into 2 equal groups. In this example, 5 out of 6 of the scores have values less than the mean. Our last measure of central tendency is the mode. The mode is the source or category that has the greatest frequency of any score in the frequency distribution. or in other words, it is the score that happens most often. The mode can be used with any scale of measurement and corresponds to an actual score in the data. If there is more than one score that occurs the most often, then there will be more than one mode. For example, if the data set were 1, 1, 2, 3, and 3, both 1 and 3 will be the modes. This figure nicely wraps up all three of our measures of central tendency as far as their recommended and not recommended uses. It demonstrates when it is appropriate to use as well as when it can be misleading. The mean is appropriate to use when you can calculate the sum of x and when you know the value of every score. The mean could be misleading if there are extreme scores, if there is a heavily skewed distribution, if there are undetermined values, if the distribution is open-ended, or if scores are in an ordinal or nominal scale. Contrastly, the median is appropriate to use when there are extreme scores, there is a skewed distribution, there are undetermined values, the distribution is open-ended, and the scores are in an ordinal scale. The median can be misleading if the scores are nominal. Lastly, the mode is recommended to be used with nominal scales, discrete variables, and when describing the shape. It is not recommended to use the mode for interval or ratio data unless you also have the mean or the mean present in the representation. With symmetrical distributions, for example, if you have 1, 2, 3, 3, 4, and 5, the mean and the median will have the same value, being 3 in the example that I just laid out. 3 is also the mode too, although if there were not exactly one value with the most frequent scores, the mode could be other numbers as well. The following are measures of central tendency for three symmetrical distributions. For a perfectly normal distribution, the mean, median, and mode are all the same. For a bimodal distribution, the mean and the median are the same, but there are two separate modes to each side of the mean and median. Lastly, the rectangular distribution has the same mean and median, but there is no mode because there is not one score that is more than any other score. Here are representations of each measure of central tendency for skewed distributions. In skewed distributions, the median tends to be the recommended measure. The graph to the left is a positive skew since the tail goes to the right. As you can see, the mode is furthest to the left where the highest frequency of scores are, then the median and the mean. The graph to the right is a negative skew since the tail goes to the left. The relationship between the measures of central tendency mirrors the positive skewed graph on the left. The mean is furthest to the left, then the median, and the mode is furthest to the right. Earlier I discussed how understanding measures of central tendency and measures of variability could aid you in understanding more complex statistics. One statistic that takes both the mean and standard deviation into play is a z-score. A z-score tells you how far a particular score is above or below the mean in standard deviation units. This could prove to be pretty useful if you wanted to explore how one individual's raw score is faring in the context of a certain group. For example, if a teacher's class average for an exam was an 80 and a student got a 76 on the exam, the instructor could calculate a z-score to get more specifics on where the student falls ranking-wise in the classroom based on the spread of scores in the classroom. On the surface, we know that 76 is below 80, but what we don't know is whether or not that student performed better than 40% or 30% of their class. Z-scores can help us with that. So in a way, all of these stats build on one another to more complex and intricate operations.